So welcome everyone to the One World Combinatorics on Words seminar. And our speaker today is Christophe Reutenauer from the Université de Québec à Montréal. And he will speak to us about Christoffel words and Sturmian determinants.
Thank you very much to invite me. And hi, everybody. I know a lot of people on the list. I have a special joke. Is this one? Can you read? Can you read what's on the blackboard? So the title is Christoffel words and Sturmian determinants. And it's a joint work with Jeff Shalit. And I want to thank especially Jean-Paul Alouche because he encouraged us several times. And so let me start now, really the talk. First, the motivation. The motivation is you take the Fibonacci word. Let's take the Fibonacci word. I just give the first, the letters 0, 1, 0, 0, 1, 0. Qu'est-ce qu'il y a après? 0, 1, 0, 0, 1, 0. Ensuite, il y a 1, 0, 0, 1, 1, 0, 0, 1, and so on. And now I choose the length of factors. Let's take 5, and I consider the 5 first factors of length 5. So I write them into a tableau. So the second one is here, and so on. I have better take my. It's here 1, 0. Ensuite, il y a 0, 0, 0, 1, 0, 1. Then 0, 1, 0, 0. I take the 5 first one. And we know that there are 6 factors of length 5. I take the 5 first one. This gives me a tableau, which is a matrix. And you can see it a matrix and as a determinant. And you can compute the determinant and you obtain 2. Of course, the example is very small, but one obtains, if I choose, one obtains n plus 1 determinants of size n by n. So we can compute these all these numbers. And of course, there is a problem of the sign because you have to choose some order on the factors. But up to the sign, we have n plus 1 numbers for each n. And the experiments have shown that in the case of the Fibonacci word, one obtains always the determinants are always Fibonacci numbers. This has been experimented, and the aim of the talk is of this work is to compute all these determinants for all Sturmian sequences. So I have a very small blackboard, but so I have to erase everything. So the first case is the the first idea was to compute, to consider Burrows-Wheeler matrices of Christoffel words, because these, and so let me introduce this. It's called Christoffel matrices. You know that a Christoffel word, we know that a Christoffel word is a word all whose conjugates are Sturmian words, finite Sturmian word. It is equivalent to the other definitions of Christoffel words. Christoffel words have many equivalent definitions, but I take this one. No, it's not quite correct. I should say conjugates of Christoffel words have this property. So we take some alphabet with ordered alphabet A smaller than B, and so premonade on this, and we take we order lexicographically, and then we take W, a word in this on this premonade, which we suppose that W is a Christoffel word. And then we form the Burrows-Wheeler matrix or tableau of W, which is the rows of this matrix are the conjugates of W, and in decreasing order. I changed this for some reason from the largest to the smallest. And the largest is the upper row, and the smallest is a lower row. This construction has been done the first time, and I mean, Burrows-Wheeler did this for any word, and in the framework of Christoffel word, this was done by first time by Mantacci, Sabrina Mantacci, Restivo, and Ciortino. They proved that in this tableau, in this matrix, the last column is increasing. It's increasing because I changed the order here. So let's, for instance, I could take a small example. Here, I put it here, is to take this word, which is it's a Christoffel word, and the largest in its conjugate class. This, you see the Burrows-Wheeler method, the words are decreasing from the upper to the lower. It's called a lower Christoffel word, and this is the upper Christoffel word. The others are conjugates. And here's an example. And you see that the last row is increasing. And these three authors, Mantacci, Restivo, Shortino, proved that this characterizes Christoffel words. The fact that it is increasing. And now, yes, I call this a Christoffel, such a matrix. We call it. It's called the Christoffel matrix. So a Christoffel matrix is the Burrows-Wheeler matrix of a Christoffel word. So I can state a result, which is rather surprising. It's a theorem we have obtained. I don't completely give details on credit because it was obtained independently from us by Zamboni, Luca Zamboni, and of course myself and Jeffrey Chalit. It was quite at the same time. It's the following. Yes, you take a commutative ring. It's better to have no zero derivatives. I mean, this is technicality, but and then we consider Christoffel matrix on this ring. Huh? This means that you take two elements of the ring and then form a Christoffel word on this two-letter alphabet, and you obtain Christoffel matrices. So the first statement is that n by n Christoffel matrices over R form a submonoid of the monoid of all matrices, n by n matrices over R. If the one which are invertible, Christoffel matrices in the group of invertible matrices form a subgroup. Of Jln of R. And the determinants, the last statement has to do with the origin and motivation. The determinant of an n by n Christoffel matrix is, we have exact formula, n minus r a plus r b multiplied by b minus a power n minus 1 and multiplied by sine of omega r. So I have to explain everything here. Where R is the number of B's in each row. A and B are the the coefficients of the matrix. It's a Christoffel matrix, so the set of coefficients has cardinality 2. So I call A and B these coefficients. I should say here that there is some order on the coefficients. I mean, I say A is smaller than B. You choose two elements of the ring, and then you choose an order on them, and then you form a Christoffel word on this alphabet, and so on. So R is the number of bees in each row. It's the same number in each row because each row is a conjugate of the others. And omega R is the sign of the permutation of Z over NZ. It's the permutation of which is multiplication by R. You are, of course, modulo n. R and n are relatively prime. When for a Christoffel words, the number of A's and number of B's are relatively prime, and so relatively prime to the length of the word. So it's a permutation of this ring, and omega R is the sign of this permutation. That's it. This is the one of the main result. I want to give a remark on omega R. Omega R is called the Zolotarev symbol. It's sometimes written like this, Rn, with a Z here. And this notation, there is, I think, a line here. And when n is odd, it's equal to the Jacobi symbol. And Jacobi symbol itself, when n is prime, odd prime if you want, it is the Legendre symbol. We have a sequence of symbols, as mathematicians like to say, Legendre symbol, which is the, you know, that Rn equals 1 if and only if R is a square modulo n. N is prime. And the Jacobi symbol was generalized to any n by Jacobi. No, Legendre symbol was generalized to any odd n by Jacobi, and the Zolotarev symbol is even more general. About these matrices, yes, we have a group. We said the Christoffel matrices form a group. And yes, I've completely forgotten to say, the group is commutative. This is quite surprising. Yes, I didn't write it on the note. The group is commutative, and Christoffel matrices commute. So commutative. And we have two results here. It's not quite completely finished. When R is a field, K with the characteristic of K does not divide N. I mean, we were especially interested characteristic 0, but it works also when the characteristic doesn't divide N. Then the group is very easy. The group is K star. R is the field K. Yes, K star by K star by the group of invertible elements. I think the group of invertible elements in the ring Z of NZ. So it's a rather easy group. And on the completely this week we have established with Jeffrey. And on the completely opposite case is when the field is Z over 2Z, then and N even, because the odd case is contained here, but in the even case, Zamboni has given the structure. It is a finite. The group of Christoffel matrices is a finite abelian group, so it's one can ask for the structure, which amounts to compute the divisors or something like this. It is there is a subtlety when n is divisible by 8. Well, I don't give the details. The papers are available on arXiv, our paper, and the one of Luca Zamboni also. So this was the first part, and the second part of the talk is about the determinants. So we have a Christoffel matrix. Its determinant is a particular case of the problem which was at the motivation at the beginning. So second part of the talk is Sturmian determinants. I have to give some notions. The first one is what's called perfectly clustering words. And the definition of perfectly clustering words is really motivated by the theorem of Mantacci, Restivo, and Shortino, which I gave before. So, perfectly clustering word. Let me write PC because it's too long. A PC word is a word on a totally ordered alphabet, whose Burrows-Wheeler matrix has its last column, sorry for my English, last column increasing. in the I take the again I say that I take the Burrows-Miller matrix in increasing order. No, in decreasing order of rows. So let me just give an example. W equals A C B, A C B, C B C, A C B, C B C, A C C. It's on the three-letter alphabet, and its matrix. It's very big. I cannot. The first row, the first word is the largest in the conjugate class, CCAC. BC, BC, Yes. It turns out that for a perfectly clustering word, the largest conjugate is the reversal. This was established by Simpson. Pretty easy. They studied these matrices. So the second largest is more. I have to CBC. And the smallest one is this one. A, C, B, C, B, C, A, C, C. So I don't write all the 9 rows, too long. And the last column is, or I can write the last column is AA, BB, and there are 1, 2, 3, 4, 5, 6 C's. AA, BB, C, 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 and there are 5 C's. Yes, and that's what. So this is a perfectly clustering word, and with an example. The second notion I need is it's called discrete interval exchanges. You take you partition the interval 1 to n into consecutive intervals, disjoint. And we do this in 2 ways. I put L here, sorry, instead of K. And we would take 2 such partitions. With L intervals, consecutive disjoint intervals, and we ask that with the I1 is equal to GL, I mean the cardinality. Cardinality of the first here is equal to that of the last. The second one is like this. The cardinality of the second one is the second one from the right, and so on. So now we map bijectively and increasingly each interval A1 onto GL, they have the same cardinalities. So there is a unique a unique bijection which is increasing. E2 goes to GL1 minus 1 and so on. This gives a permutation. This defines a permutation of Sn in Sn, and which this is called a discrete interval exchange. Let me take an example. E1 equals 0, 1. E2 equals 2, 3. E3 is equal to 4, 5, 6, 7, and 8. And J1 must be of the same cardinality of the last one, so cardinality 5. So J1 is 0, 1, 2, 3, 4. Apparently I've changed here I take instead of, I should have taken 0 n minus 1. I have a little shift on the indices. J2 is equal to 5, 6, and J3 is equal to 7, 8. So you can see the permutation. Sigma is equal to, I think there is a problem here. 0, 1, 2, 3, 4, 5, 6, 7, 8. Ah, yes, no, it's okay. So sigma, so I have 7, 8. This sigma is here. And you can see these here the separations. And you see the two intervals, the i's and the j's. And sigma is called circular if it is a long cycle. And it's this one which we are interested in. And here we have, it is the one I have here, it is circular. You write it as a cycle, starting from 0. 0 goes to 7, 7, 3, 3, 6, 6, 2, 5, 5, 1, 1, 8, 8, 4, and 4, 0. So it's a long cycle. And now you encode this cycle by 3 letters, by ABC. Perhaps I put it here. Encode sigma by ABC, where E1, each digit, 0 and 1 here, of A1 are coded by A. Each digit of A2, each element of E2 is coded by B, and I3 is coded by C. So the word I obtain I encode the cycle. So I have here A and A. B corresponds to 2 and 3. So B, and the other are C. And this And we recover the word we had before in the first section, section 2, 2.1, 2.1, 1. And this corresponds to a theorem. The theorem is due to Ferenczi and Zamboni. It said that a linded word, I consider a linded word is perfectly clustering if and only if it is the encoding of some circular, that is important, discrete interval exchange. And these words exist on any alphabet, totally ordered alphabet. And in the two-letter alphabet case, these are exactly the Christoffel words. This is, which is, yes, it's exactly because of the theorem of Mantacci, Restivo, and Shortino. I just want to have number 37. Yes. You see that, let me just give a remark. You see that to have a discrete interval exchange, it is it's equivalent to have a composition of n. That is a way of writing n as a sum of integers. Here it's 2 plus 2 plus 5. And if you know this composition, you have the intervals i's and the interval j's are completely determined. However, it's difficult to know if such an interval exchange is circular. This is known as sigma. Sigma is completely determined by the composition, cardinality of E1, cardinality of E2, and cardinality of EL. But when L equals 2, it is circular if and only if there are two intervals, the two numbers are relatively prime. Let me use the orthogonal notation. The cardinality of E1 is orthogonal to, is a relatively prime to E2. This is known from the theory of Christoffel words and so on. When N equals 3, it is also, there is also a criterion circular if and only if E1 plus E2 is relative prime with E2 plus E3. And this was proved by Pak, Igor Pak, and Redlich. And they proved also a very nice result that the density of circular is, I mean, the density of circular interval, discrete interval exchanges among all discrete interval exchanges is 6 over p squared when n tends to infinity. And in general, no criterion is known. No criterion is known, and even there is a result, but I have forgotten the name of the authors, which prove that in some sense there is no arithmetical criterion. However, the construction of all these circular discrete interval exchanges was done by Mélodie Lapointe. So let me finish this introduction of notions and give now the main theorem. And I will be very informal. The main theorem is about the determinants. Given a Sturmian sequence, or Sturmian word, if you prefer, infinite word, on 0, 1, and we did it on 0, 1, but I think it can be generalized. The n plus 1 determinants of order n obtained from the n plus 1 factors. I say factors instead of subwords. I am the Lothair school, we say factory for connected subwords. The n plus 1 factors of length n, in some order, there is some order which I skip the details, lexicographically ordered. It is, this should be explained more precisely, but I don't want to give it now. So you have a length, we choose length n, we have n plus 1 factors, we put them, and so choosing n of m, n of them, we have a determinant, and we have n plus 1 choices, and this gives us a vector of length n plus 1. And the remarkable fact is that these vectors form a perfectly clustering word which I call Vn on a 2 or 3 letter alphabet. Two or 3 letter alphabet, which is the alphabet is a subset of Z, because the determinants, this is not surprising. The determinants, the matrices are matrices of 0, 1. If when you compute the determinants, you obtain an integer. So the alphabet is always a subset of Z, which has cardinality 2 or 3. And we can say when it's 2 and when it's 3. And it is a 2 letter alphabet if and only if n, the length, the n I have here, is equal to length of w minus 1, where w is a Christoffel word which is a factor of the sequence, our Sturmian sequence, -1. And this is equivalent to say that n equals p plus q minus 1, where q over p is a semi-convergent of the slope of the sequence. Now, this is the case where there are only two, where for a given n, there are only two values of determinants. Otherwise, there are three. And in the other cases, it is a three-letter alphabet. And one letter of which is the sum of the two others. This is the main theorem. And I want to conclude with Fibonacci, which was the original motivation. What happens with Fibonacci? I will not give, it's a little bit technical. Fibonacci a Fibonacci word. So plus or minus Vn, there's always a problem with the sign, is Vn, I recall that Vn is the word you obtain by taking all the n by n determinants of order, all the n by n determinants of associated to the Fibonacci sequence by taking n factors of length n. And so it's a word of length n plus 1. Plus or minus Vn is the perfectly clustering word associated with the composition composition. There are two cases. Nu is even. What is nu? I explain. The composition is f nu plus 1 minus I f nu plus 2 minus I. And this is the composition. And over the alphabet, the alphabet is minus f nu minus f nu minus 2, f nu minus 1. This is when nu is even. And what is nu? Nu is defined by the condition that n, our n, is in between these two numbers. And I is the difference There is also if new odd, I don't give the details. It's very similar. Well, it's technical, but at least you can see that this one, the middle number here, is the sum of the two others. Just let me the computation of the sign has been, we have computation to compute the sign. It's not very easy. I mean, it amounts to compute the Zolotarev symbol. But in this case, we have done it. It is the Zolotarev symbol. So F it's a new here, new plus one, which I recall you that it is the multiplication by F nu plus 1 modulo F nu plus 3, and in the, yes, and the sign and even the cycle type, or anyway, the cycle type of this permutation is maybe computed using Fibonacci and Lucas number. That's all for my talk. Thank you very much.
Thank you, Christophe. We can take some questions. There was one question in the chat. I can ask it now. Given a Linden word W that encodes an interval exchange, is there a clear relation between the interval exchange and the standard permutation of W?
Yes. I'm always puzzled because I know this very well, but I cannot completely. Ça marche comment déjà ce truc de Linden word? Yes, answer is yes. I could not give the details exactly now, but if Esteban wants, I can write it the exact details.
All right. Jean-Paul, you have a question?
Yes, please. This is a vague question. Namely, is it possible that there is a relation between the PC, what was it? Perfectly clustering words and the sequences with grouped factors by Cassagna?
Group fact. I don't know what this.
As far as I remember, it's a sequence, an infinite sequence in which all lengths of all factors of given lengths occur consecutively. So, of course, for general sequence, there is nothing to say, but maybe for Sturmian sequence, there is some sort of relation. I'm not sure. That's just a vague question, actually. Yeah.
Yes. I don't know.
Okay, merci. Thank you.
But it reminds me a question which I find interesting is, given the Sturmian sequence, in which order occur the factors of length n? Because I have, at the very beginning example, I gave the 5 first factors of Fibonacci sequence, and then I don't know why there is it's natural to order them lexicographically, but they don't appear in this order in general.
Yeah, it might be related. I mean, the difference is possibly that in your case, you have an order, And in the Cassane case, there is no order. I mean, just you look at the first occurrence of factor or something. So maybe it's not related. I'm not sure. Okay, I have to see that in more details. Merci. Yeah.
Thank you, Jean-Paul. Gabriele.
Pami?
Yes. Christophe, thank you. I have a question about the last result that you showed. Is there a relation between this result and the three distance theorem? Because it seems related.
Yes, of course, everybody, we have there is the relation is just formula. I don't know something deep, but I suspect there should be something because it cannot be a hasard. It cannot be just a coincidence. I could not relate it really. I didn't try very hard, I must say, but I know that three distance theorem is really very strongly related to perfectly clustering words on three-letter alphabet. I have done work with Valérie Berthet, which reproves the one proof more, of course, of this three distance theorem in the rational case, and which is actually the interesting case. And but I don't know. My answer is very vague.
It's interesting. And then I have a question about the terminology. I understand that you reverse the order of the rows in the BWT matrix to have the identity matrix in the groove.
Exactly.
But do you have a name for the biggest conjugate in a conjugacy class of a primitive word? Because the least conjugate is a Linden word, but what is the name for the biggest conjugate? Do you have a name
there
for
is
it?
no official terminology.
Okay.
It's a Linden word on the opposite order, for the opposite order. There is no, you should ask Dominique Perrin, who is the master of the terminology. I think he's no more here, or
Thank you.
Thank you. Does anyone else have any questions for Christophe? Okay, if not, thank you again, Christophe, for a very nice talk.